Hi everyone, my name is Susanne Bornelöv and I work as a Senior Research Associate in the HANO Lab at the University of Cambridge, and I'm delighted to give this poster presentation on behalf of the CANformers team describing our submission to the DREAM Challenge 2022. So the title of the challenge was Predicting Gene Expression Using Millions of Random Promoter Sequences, and the task was to train a sequence-to-expression model using provided 6.7 million random promoter sequences. And the data was in the format of 110 nucleotide sequences paired with expression values that had been measured through SORT-seq, which is a massive parallel reporter assay, as shown here. And the challenge evaluation was done on 71,000 unseen sequences that had been measured in a separate experiment, but using the same technology. So there were more than 100 teams participating, and our team finished in 4th place. So for the data representation, we used a traditional one-hot encoding. We then excluded sequences with too many missing bases or with too unusual length of the sequence. For most of the training and the hyperparameter optimization, we divided the data into a training, a validation, and a test set. However, once we found a promising model and we wanted to submit it to the leaderboard, and also for the final challenge submission, we omitted the test set and we retrained the model, allowing us to use 1 million extra training examples. So this is the final model that we submitted, but it should be said that we have around 10 quite different models that all performed more or less equally well. So this one had 6 convolutional blocks, where we have residual connections allowing the model to bypass the 2nd, the 4th, and the 6th block. And these convolutional layers are fed into dense layers, where we had 2 linear blocks and 1 linear output layer. And in general, we found that adding convolutional layers up to perhaps 6 or 7 layers improved the model. And for the linear blocks, we generally found that having 1 linear block was optimal, but for this particular model, we got better performance with 2 blocks. So this model had 16 or almost 17 million trainable parameters, but some of the models were much smaller with as little as 1.4 million parameters, suggesting that the model can be quite a bit smaller with almost equal performance. So this is an output of the model training for the final submitted model. So we can see the number of epochs, and we can see the training and the validation loss, Pearson correlation, and Spearman correlation. And we used an early stopping criteria where we looked at the Pearson and the Spearman correlation in the validation set, and we selected the epoch giving the highest average correlation. So in this case, this was epoch 24, and this is the performance on the validation set for this particular model. That was the final one that we submitted. So we can see that we have a good correlation between the measured expression and the predicted expression. We do, however, have these lines of data points at integer values representing the shallow sequencing of the training data. So a little bit about model fine-tuning. So we use the Optuna framework for hyperparameter optimization, and we allowed it to change both traditional hyperparameters as well as many model parameters as possible. And we did run this for many different kind of starting points or different models, including convolutional models, transformer models, and models with residual connections. The main conclusion from this was that most of these runs, if we allow them to change the max pooling operation, was that they preferred to have a max pooling operation at the penultimate layer, and they preferred to have a single max pooling operation. And this seemed to improve most models regardless of the overall design. We tried many things that didn't particularly work as well, at least not in our hands. So one challenge that we had was that our models performed really well on the public leaderboard in terms of the Spearman correlation, where we were usually around the 2nd or the 3rd place, but we performed less good on the Pearson correlation. So we thought that if we could somehow change the target value distribution, we might perform better in terms of Pearson correlation. And we tried, for instance, quantile normalization of the expression values, but we didn't see any improvement. And if anyone is interested in discussing any of the other approaches we tried, then feel free to reach out. So a little bit of a performance breakdown of our final submission. So the models were evaluated both using all sequences, but also using sequences of particular characteristics. And then these were summed using different weights into different scores that were then averaged. So as you can see, our model performed well across all different categories. And we performed particularly well of the challenging sequences, which are sequences where a previously trained biochemical model and convolutional model had the highest disagreements. So this perhaps shows that our model is reasonably good across different type of sequences, which was also reflected in our overall 4th place. So in terms of correlation values, as expected, we performed best on random sequences, which is the type of data that the model was trained on, and also how the loss function was calculated during training. So our model was blind to whether any of the sequences could potentially belong to any of the categories. So with that, I would like to thank you all for listening, and please don't hesitate to reach out if you have any comments or any questions.